Hey guys, welcome back to Chapter 4. We're going to be continuing on with 4.4, Conditional Probability and Independence. The probability of an event A given that event B has occurred is called the conditional probability of event A given B. And that's denoted as this. So that is pronounced A given, that line is a given, B. Further, the probability is defined as this. That's the probability of A given B is equal to the probability of the intersection of A and B, or probability of A and B, all over the probability of B. Likewise, probability of B given A is equal to the intersection over the probability of A. Independence of events. Two events A and B are said to be independent if and only if the probability of A given B is equal to the probability of B. And that's to say that, like, if B has occurred, did it affect A? And if the probability of A given B is the same as the probability of A, then clearly no, B having occurred didn't affect A. That's the idea behind independence, using the conditional probability and equating it to the probability of A. Where both probability of A and B are greater than 0, yep, that's true, and this is equivalent for the other way. The probability of B given A is equal to the probability of B. I would go ahead and add in another rule there, and then this would just be a check for independence, and this check for independence would be the probability of A times probability of B equals probability of A and B, the intersection. And I put a question mark there. So this is basically saying that the way that we check for independence is that if the probability of A times the probability of B equals the intersection, then independent. I know I missed some letters there. Independent. We'll see that in some problems here in a second. And then we move on to the multiplication rule. Don't let all the letters scare you here. This multiplication rule is just exactly our conditional rule that we just looked at. This rule. So the conditional probability, so probability of A given B is equal to the intersection of A and B divided by probability of B. If we go back here, I guess I'll write it right here. Probability of A and B is equal to the probability of A times the probability of B given A. And if we just divided the probability of A out of this, so we just divided the probability of A out of this, it would be the probability of A and B all over probability of A is equal to the probability of B given A. And that's our exact formula from down here. So this whole thing, and then I guess don't mind this last part. This last part is the same thing. Also, they're just combining the two formulas together. All this is saying is this multiplication rule is just using this conditional probability rule, either one of these, because they're equivalent. We're just talking about two different events. Just using that and rearranging the terms to solve for the probability of A and B, or the intersection. Okay. And then this is just the rule that I noted before. If A and B are independent, then the probability of A and B will occur. The intersection is equal to the probability of A times the probability of B, or the probability of B times probability of A, all the same. And then furthermore, for n independent events, so not just two events, so this is just for two events. And this is just takes it up to n number of events. And this would just say that the intersection of all those events right here, that's the intersection, is equal to all of the probabilities multiplied together. That's all that means. Okay, let's look at our worksheet. We're going to look at problem 2. Wrong one. Problem 2. Using the above table, so this will be the table that we just used in the last video. Find the proportion of MasterCard holders who have Visa cards. Interpret and write this proportion as a conditional probability. So this is where the wording gets pretty dicey, I guess. What the mind wants to do whenever you read this, you want to turn this into like an and, M and V, so MasterCard and Visa card. But that's not actually what's going on. So it says find the proportion of MasterCard holders. The word of is very important. Of MasterCard holders who have Visa cards. So I could word this differently. I could say find the proportion of, or find the proportion who have Visa cards given that they have MasterCards. And that means the exact same thing. So we would write given M, V. So that's what that would look like. Find the proportion of MasterCard holders. So given that they're a MasterCard holder, the probability that they are a Visa card holder. That's an arrow, not a T. And so then we would write down our formula, and that would just be the joint probability, or the intersection. That's V and M, probability of V and M, all over the probability of M. So these are numbers that we have already calculated. I'll let you guys scroll up if you want to scroll up, but it's just too hard for me to scroll back and forth. I'll just look at my notes here. Uh-oh. It's 1,000 over 2,500. Excuse me, and that is 0.4. So this is given that the person is a MasterCard holder. So given that the person is a MasterCard holder, the probability that they also have a Visa. So we would look at the 2,500 here and the 1,000 here. And it's going to be 1,000 over 2,500, essentially. 1,000 over 2,500. So essentially we would be like disregarding everything else in the table that doesn't have anything to do with MasterCard. So once we say given M, that's kind of what we can do with the whole table, right? So we would just be looking at that top line. And so then our total is 2,500. And then the people that have a Visa are 1,000. And that's it. So then similarly, so that was part A. So then for part B, it says find the proportion of Visa card holders who have MasterCards. So given that they have a Visa, what's the proportion that they have a MasterCard? So given that they have a Visa, what's the proportion that they have a MasterCard? So this formula we know as the probability of M and V, right? Which is just the probability of V and M. Those are interchangeable, but we'll write it just so that we don't get confused. All over the probability of V. And that's going to be 1,000, which, like I said, M and V is the same as V and M. So it's going to be the same 1,000 over the number of people who have who have Visa cards. So we scroll back up, and the number of people who have Visa cards are right here. So similarly to last time, once we say given that they have a Visa, we can just focus in on this column right here and just get rid of everything else in the table from our thought process. And so then it would just be 1,000 over 4,000. or 25%. So then, lastly, for this question, are the events having a MasterCard and having a Visa independent? Justify your answer. So, independence, like I said, the easiest way to answer the independence question is when we multiply their marginal probabilities together, do they equal their joint probabilities? That was the formula of, I'll just go ahead and sub in M's and V's here. So we'll say probability of M times probability of V, and then question mark, does that equal probability of M and V? Okay, so we have all these numbers. We've calculated all these numbers before. And we know that probability of M is 0.25. Probability of V is 0.40. And the probability of M and V is 0.10. So we go ahead and we multiply the left side of this, and 0.25 times 0.40 is in fact 0.10. And those do equal, so we say yes, independent. So it'll take us to Bayes' theorem next, which Bayes' theorem, yeah, go ahead and read that slide just for a second. So not quite sure why the book wants us to learn Bayes' theorem. So yeah, but I'll teach it to you guys, and then we're going to go ahead and we're just going to use contingency tables to solve any issue or any problems that we have with Bayes' theorem. So I'll go ahead and read this. I'll go ahead and read this slide off, just to reiterate. So, like, I'm going to go through this, but anytime you see a problem that resembles Bayes' theorem, I want you to use a contingency table to solve the problem, because I think you'll just save yourself a world of headache. All right. So I'll go ahead and read this off, and we can get into it. And I'll try my best to explain. I'll try my best to explain. I guess what they're kind of saying here. S1, S2 through SK represent K mutually exclusive possible states of nature, one of which must be true. Probability of S1, probability of S2, all the way up through the probability of SK represents the prior probabilities of the K possible states of nature. If E is a particular outcome of an experiment designed to determine which is the true state of nature, then the posterior or revised probability of a state S sub I given the experimental outcome E is calculated using the formula on the next slide, or on, I guess, on this slide. So, first thing, let's break this down into the three different parts that it is. The first formula we see, this probability of S sub I given E is equal to the joint probability or the intersection probability of S sub I and E all over the probability of E. That's just our regular conditional probability that we just learned. So that would be the probability of A given B is equal to probability of A and B over the probability of B. So that's just that, and they are subbing in S sub I for A and E for B. So that's fair. That's something that we can work with. But then they get into defining the top, the probability, I'll just write it up here, the probability of A and B. They look at it like the probability of B and A, which is the same thing still, but then they want to go back and use the multiplication rule, and they want to say that it is the probability of B times the probability of A, or sorry, the probability of A times the probability of B given A. And then they sub in, so they're going to be using this term to sub in for the top here eventually. And all the while A is going to be S sub I, and B is going to be E. So they use the multiplication rule to sub in for the top here. So now this whole thing is probability of S sub I given E is equal to the probability of S sub I times the probability of E given S sub I over the probability of E. And then, so we have the top here. The top stays the top, and that's that. And we got that from the multiplication rule. But then what happens down below is the thing that I think is the hardest to follow. So we've talked about this E, which is this particular outcome up here. And they define E as the summation of all of the possible states of nature that E could occur in. So this is again using the conditional rule, but made really tough to understand. So E can occur in S1 state of nature, S2 state of nature, S3, all the way up to SK. Okay, so it can occur in all of those states of natures. And so the way that we would calculate then what the total probability of E is by calculating the probability of the state of nature and then calculating the probability of E given that state of nature. So that's what we have here. So the probability of S1 times probability of E given S1, and then the probability of S2 times the probability of E given S2, all the way up through SK. Okay? I think that it might be a little clearer when we do problem 3 here. And if it's not, I guess ask questions. But if you don't want to ask questions, that's fine. We're going to solve this using a contingency table as well. And that's what I would use. I would never use this formula ever. This formula is miserable. And I just think really, really difficult to understand. So I would use contingency table. I'll show you how to solve both ways. I think the contingency table is way more intuitive. But yeah, so let's get on to that. So we'll go over to worksheet problem number 3. And I'll probably need a lot more space for this, I would imagine. Okay. So a department store is considering a new credit card policy to try to reduce the number of customers defaulting on payments. A suggestion is made to discontinue credit to any customer who has been 1 week or more late with his or her payment at least twice. So that's kind of confusing, but let's just call that late. We'll just call that L. Past records show, and so then the thing that we are trying to determine is defaulting. Okay. Past records show, and so sorry to keep stopping, but this is the way that I'm going to attack problems from now on, is I'm going to read through them and I'm going to pull out all of the information that we have and try to write it down, kind of before we get started. A suggestion is made to discontinue credit to any customer who has been 1 week or more late with his or her payment at least twice. So considered late. Past records show 95% of defaults were late at least twice. Okay, 95% of defaults were late at least twice. So that would be saying, given that we have a default, 95% are late. So that would be the probability of late given that we have a default. and that's 0.95. Also, 3% of all customers default. So that would be the probability of default. Just in general, the marginal probability is 0.03. And then lastly, and 30% of those who have not defaulted have had at least 2 late payments. So the 2 late payments is, again, our definition of L. Okay, so I'll read that again. And 30% of those who have not defaulted. So given that they have not defaulted, they've had at least 2 late payments, so L. So that would be probability of, given that they haven't defaulted, L. 0.30. So again, I guess what I'll first do is I will write down, just based upon what we have, I'll write down, I guess, what else we know. We know that given the complement rule, that the total probability of any sample space is going to be 1. So we know just in general that the total probability of any sample space is going to be 1. So we know that we can say 1 minus the probability of any event is going to be the complement of that event, and that's just going to be, so we'll say probability of D complement, so not defaulting, is going to be 1 minus 0.03, or 0.97. Okay, so if we decide to use, so let's read the question first. Find the probability that a customer with at least 2 payments will default. So what is that asking? So given that they have 2 late payments, the probability that they'll default. So this is the probability in question. So I'll just say question, or I guess we can just say A. The probability, given that they have at least 2 late payments, probability that they will default. So this is going to harken back to Bayes' theorem. And we're going to go apply that formula. So if you are following along in the PowerPoint slides or in your notes, go look at Bayes' theorem. And Bayes' theorem, if we apply D and L to it, is going to give us the probability of D times the probability of L given D all over the probability of D times, sometimes I put the dots in there for times, sometimes I don't, probability of L given D, so the exact same thing, plus the other state of nature and its likelihood, which would be the probability of not D times the probability of L given not D. And then the one thing you'll notice is we have all these probabilities. So we want to know what this is, probability of D given L. We have this, 0.03. We have this, 0.95. This, we have 0.03. That, 0.95. This, 0.97. And this, 0.30. So 0.03 times 0.95 all over 0.03 times 0.95 plus 0.97 times 0.3 is equal to 0.0285 all over 0.0285 plus 0.291, 0.0285 all over, no, we don't have to do that. We'll just call this whole thing equals 0.0892. So that's using Bayes' theorem to solve the problem. Okay, so on the bottom portion of it, we list off all the states and natures that L can occur in. We give the probability of that state of nature, and then we give the probability of L given that state of nature. And we add up all those and then we take what we're actually looking for at the top. Okay, so that's, yeah, so I guess that's one way to do it. That's the Bayes theorem way to do it. But now I'm going to show you how to, if I can get my word processing skills on point, I'm going to show you how to do this with a contingency table, which I think is much easier. So I'll just first form a contingency table, and the contingency table will be D, not D, L, not L. So we write down what we know. One, we know that the total probability is equal to 1 in any scenario. And then the only things that are going to be in the contingency table already are, from the problem, is going to be the marginal probability of the percentage of defaults, so 3%. So the probability of D, which is equal to 0.03. So that's what we can put in here. So we go over to where we know that the marginal probability is, and that is 0.03. Okay? And then we deduced that, well, if we have a total probability of 1 and 0.03 in D, then we know that this is going to be 0.97. And that's what we calculated in the first part there. So, how do we fill in the rest of this contingency table? Well, as I mentioned before, the inner portions of the contingency table, those are all intersections. Okay? And the formula for an intersection, which we just learned, is the multiplication rule, which really we know is the conditional rule, just kind of refigured. We would be using a conditional probability and a marginal probability to come up with the intersection. Well, we have conditional probabilities given to us in this problem. So we are going to use those conditional probabilities that we have in order to fill in the table. So we see these conditional probabilities that we have, and we are going to go ahead and solve for our intersections. So we know that given the multiplication rule, or I guess I generally like to use the conditional rule because that's, to me, the easiest to remember. So I'll just say we know that, and this is pretty much an easier way to think about it, I think, in terms of I guess using what we have. So we would use what we have. So the first thing that we have in conditional probability is probability of L given D, and that's 0.95. Okay, so we plug that into the formula. We'd say probability of L given D. We plug that into our conditional probability formula, and we know that that is equal to the probability of L and D all over probability of D. So the unknowns, the only unknown here is this intersection. We have the probability of L given D, which is 0.95, and we have the probability of D, which is 0.03. So in order to find the probability of L and D, we multiply, we multiply both sides by 0.03. So we get 0.95 times 0.03 in order to find our intersection probability, and that is going to give us 0.0285. Okay, and we will move down again, noting that the other conditional probability that we have is probability of L given not D, and we know that that is equal to 0.3. So we would write that into our conditional probability form. So L given not D is going to be equal to the probability of L and not D all over probability of not D. Again, we look up, or we try to look to see what we have. We know that we have this. It's equal to 0.30. We know that we have calculated this. That's equal to 0.97. And then this is the only unknown. So in order to find, I don't know, I put an equal there. In order to find out what the intersection probability is, the probability of L and not D, we multiply 0.3 times 0.97. And we get, why am I not seeing what we get here? We get 0.291. So L and not D. So L right here, not D right here. Their intersection is right there. And we get 0.291. Okay, and from this point, we can fill in the rest of the table because we have enough information to do so. So we add up this probability and this probability. And then underneath it, we're going to get, to find the marginal probabilities, we're going to get 3195. And then we can say 1 minus this probability to get what this probability is, and we get 0.6805. And then we know that the total is 0.97 right here, and we can minus off this 0.291 to get this 0.679. And then we can do it either way. We can say 0.03 minus this 0.0285 for that, or we can say 0.6805 minus this 0.679, and it's going to give us the same thing either way, which is 0.0015. And that's that. So now we've solved the whole contingency table. All right. So if we would like to know what our answer is for A, so what is the probability? I mean, as you can guess by my lead up to this, we know we're going to get this right. Probability of D given L is equal to the probability of D and L all over. So this is just our general conditional form. Probability of D and L all over probability of L. We look here, the probability of L is 0.3195, the marginal probability. The probability of D and L is 0.0285. 0.0285 divided by 0.3195 is what we have up here, 0.0892. So that's A. So we can solve it either way. So using the contingency table is considerably more work, but in the end, you just have all the numbers, and realistically, you're like ready to answer any question that they have because you just have all of the numbers. Whereas Bayes' theorem, you have to point it at a specific question. But the contingency table, you go ahead and solve that before you even know what the question is asked, and then you can go ahead and answer any question you want. So we come up here, based on part A, should the policy be adopted? And I would go ahead and say, yes, the policy should be adopted because the probability of D given L, so we know the probability of D given L is 0.092, we'll say almost 9%. That's greater than the probability of D. The probability of D is 0.03. So given that somebody has been late on a payment twice or more, their likelihood of default goes up to 9%, whereas just the general population, their likelihood of default is only 3%. So based upon Part A, or based upon that information, yes, the policy to discontinue people who have been late more than twice should be adopted because we can see that those people are defaulting more than the general population. All right, guys, I know that was a lot. I'm sorry that we had to do Bayes' theorem, but I'm glad that we got to look at the contingency tables. This might be a chapter where you're really going to want to look at the review that I put up. We're going to go through this again. Let me know if you'd like to see more Bayes theorem. I don't want to do another Bayes theorem problem using Bayes theorem. I would much rather just go through the contingency table method and do it that way. I think that that's the most beneficial thing for you. So yeah, I'll conclude this video here and then on to the next video for chapter 4. All right, thanks so much, guys. Take care.